All right, so remind us, we're just going to run through some of this. Remind me, what is the Pythagorean theorem again? Can only be used on right triangles. So only used for right triangles. Can be used to find a missing it's a missing side. So you can only use it to find missing sides. So in trig, when you get into like sine, cosine, tangent, all that stuff, you can find sides or angles, but Pythagorean theorem just sides. And the side lengths, if possible, you should simplify, right? Simplify. And the actual Pythagorean theorem says a squared plus b squared equals c squared. All right, so on these first three here, you're just using the Pythagorean theorem, nothing fancy, right? So this first one you did, 4 squared plus 6 squared equaled x squared. And so then you had x squared was equal to, what was that? 52. So then x was the square root of 52. And you simplified that. What was the perfect square that went into 52? Yeah, or like, how did you simplify square root of 52?
2 times the square root of 13.
So 2 times the square root of 13. So 52 was 4 times 13. And then the 4 came out as a 2, so x is 2 square root of 13. Perfect. And the middle one was slightly different, right? Because we had the hypotenuse in this case. And so this would have been x squared plus 9 squared equal to 12 squared. And so you had x squared equals 63. So x was the square root of 63. And that simplified to 3 square root of 7, because 63 was 9 times 7. Perfect. And then last but not least, this is actually a very special triangle. It's a right triangle, but it has two side lengths that are the same, right? And so we're actually going to talk about this in more detail. But you can just Pythagorean theorem. 6 squared plus 6 squared equals x squared plus x squared. So it ended up being x squared was 72, right? And so when you simplified, x got
2 square root of 18.
2 square root of 18. Now the problem with this is 18 still has a perfect square in it, doesn't it? Yeah, so if you simplify and then you look at the number at the end and you still have a perfect square, you just have to keep going. So don't go back or anything, just press on, right? Perfect square in 18? It's 9 times 2, right? 9 times 2. And then 9 comes out as what's the square root of 9? 3, so it'll multiply with the 2 in the front to be 6 square root of 2. So if you simplify and then you realize that your radical still has a perfect square in it, just keep going. It meant that you didn't take the biggest one out at the beginning, but you don't have to go backwards. The nice thing is you can just press on, right? All right, so Pythagorean theorem, just kind of in general, feeling all right about that. So up next, we're going to talk about Pythagorean triples. Have you ever heard of a Pythagorean triple before? Yeah, so these are the nice numbers, right? Like we like to call them. It's when you have two sides and your hypotenuse is a nice number. Instead of being like a square root of something, you're just going to get an integer at the end. So the most common one is the 3, 4, 5, the 3, 4, 5 triangle. And so the most basic, most common, the one that will probably appear on the ACT, right, is the 3, 4, 5. And then you can technically take the 3, 4, 5 and multiply it by scale factors, and you'll still get really nice triangles. So this triangle right here, we have a 6 and a 10, and so what happened was this one got times by 2. The 3 became a 6, the 5 became a 10. So that other side, 4, becomes a 8. So yeah, without doing the Pythagorean theorem, if you recognize the 3, 4, 5, you can go ahead and just use a scale factor to help you. The good news is, though, is if you don't recognize it, you can always just Pythagorean theorem, right? All right, so the next one, we have 30, which would be 5 times 6, right? And then here we have 24, which is 4 times 6. So this is a times by 6 scale factor. So that would make the other side 3 times 6, and 3 times 6 is
12.
close.
18.
18.
Oh my God.
It's been a while. It's all good. 18, right?
I've been doing like complex math so long. Basic math.
No, that happens to me too. Sometimes I'm like, wait, that's an easy calculation. What is it? Or like, I'll just do it wrong because I'm thinking 5 steps down the road. So I get it. It happens. All right, so always be on the lookout for 3, 4, 5s. Those can just make your life easier. The nice thing is if you forget, though, Pythagorean Theorem will work. The next one is a 512. Do you know what the hypotenuse is in a 512?
No.
No, so Pythagorean Theorem it real fast. And it will tell you.
Thirteen.
13. So a 5, 12, 13 is the next Pythagorean triple. In terms of the smallest leg just going up. So 5, 12, 13. And once again, you can do any scale factors of the 5, 12, 13. So this one right here, the 5 becomes a 10, the 13 becomes a 26. So the scale factor here was times by 2. So then the 12 would times by 2 to get 24. This one's a little bit harder to see. 5 became 2.5. The 13 became 6.5. So what's happening here? It's dividing by 2, right? Cutting it in half, which technically is the same as multiplying by a half, right? So technically your scale factor here is a half. And so then you would take the 12 and cut it in half and you would have 6. All right, and then the next Pythagorean triple is a 7, 24, and then see if you can figure out, do you know what it is? No? So Pythagorean Theorem, see if you can figure it out. $25. 7, 24, 25. All right, so what happened to go from the normal 7, 24, 25 to get to the second triangle? Yeah, they were being times by 2 again. So that means that 7 became 14, 25 became 50, so 24 becomes a 48, yeah. The scale factored ones are the hardest ones to kind of recognize. This next one, what happened here? We have 24 to 144 and 25 to 150. I would go with the 25 to 150. What happens 25 to 150? What do we times by? Think about quarters. How many quarters are in $1.50? Mm-hmm. 6. There are 6. So that one got times by 6. 24 times 6, you can check, is 144. So that's how you know that there is a scale factor there. So this side would just be 7 times 6, and 7 times 6 is 42. So if you recognize your Pythagorean triples and you know that they're in there, it can make them go a lot faster for sure. There's a bunch of other ones. So the 3, 4, 5 most common. The 5, 12, 13 is the second most common after that. And then they start to get a little bit more obscure. 7, 24, 25, 8, 15. Any guesses? 8, 15. Actually, it's not. No. Yeah. Look at this one. This went 3, 4, 5. 5, 12, 13. 7, 24, 25. So you would think 16 is actually 17 if you were to Pythagorean theorem, yeah. But then if you go to the next one, 940, this one is 41. It is 41. And then the next one, 1160, that one would be 61. And then the last one, 1235, you would think 36, but it's actually 37. I know, it is weird, but here, we're going to investigate as to why that's true. So this one was different, and this one was different. So I'm going to highlight them. So when your smallest leg was 8 and 12, we went up by 2 instead of up by 1. All the other ones, the smallest legs, 3, 5, 7, 9, 11, all went up by 1. So do you see any patterns that could possibly help with that? Between those numbers?
No, wait. If they're even, if like the smallest leg is even, they go up by 2.
Exactly. If your smallest leg is even, 8 and 12, the only two even numbers on our list, the hypotenuse went up by 2 from the longest leg. If they were odd, the smallest leg was odd, then the largest leg just went up by 1 to get the hypotenuse. Yeah, there's a huge connection there for sure. And so that's kind of interesting, isn't it? That either it goes up by 1 or it goes up by 2, depending on if the smallest leg was even or odd. Really, I think the easiest way to recognize some of these upper ones is if you have these two numbers. So if you have a hypotenuse and a side that's only 1 digit apart, in my brain, I'm thinking, oh, maybe that's a Pythagorean triple going on there. Really, though, if you can recognize the first two and their scale factors, that's going to make your life a lot easier. A lot easier, for sure. You have any questions, Pythagorean triples? No. There's a bunch more. We just don't get into all of the details. All right, so we're going to talk now about these special right triangles. And so there's two kinds of special right triangles, and these are kind of like the foundation of what a lot of trig is built off of. They're built off of these two triangles. So all of trigonometry being like triangle, right? So you can build them off of all different types of triangles, but these two are like the ones that are the most common. Like we use them all the time. We're going to be talking about 45, 90s, and we're going to be using what comes from them quite often. Yeah. So here's the first one, 45, 90. It is what we call a right triangle, right, because of the 90 degree. And then because the other two angles are the same, it makes your two sides the same. And so it's actually an isosceles right triangle specifically. And this one is the easiest of the two, in my opinion. So whatever one of your side lengths is, the other side length is exactly the same. And then the hypotenuse is whatever that number was, but times by the square root of 2. So for example, this first one, 2, that gives us 2, that's a side length, right? So that means B has to be 2 because that's the other side. And they tell us it's a 45, 90. So then A is going to be 2, the side length, times the square root of 2. So that side would be 2 square root of 2. Yeah. So on number 3, it's also 45, 90. 3 square root of 3 is the side length, right? So what's the other side, the V? 3 square root of 3, yeah, it's the same thing. And then to get your hypotenuse, what do you have to do?
3 square root of 3 square root of 3?
3 square root of 3, not square root of 3, but square root of 2, because it's always times the square root of 2. Oh. Yes. So take whatever the side was, times it by the square root of 2. And you can actually simplify this. 3 square root of 3 times 2, the square root of 2.
Square root of 6.
Yeah, 3 square root of 6. So your hypotenuse is 3 square root of 6. The nice thing is technically if you know one side and you're good with the other, you could just have Pythagorean Theorem, right, to find the last one. But the goal is to not have to use the Pythagorean Theorem on all of the special cases. It's to recognize specific things about them. All right, so number 3 is a little bit trickier because I give you this side here, and that side is the hypotenuse, isn't it? Yeah, so how do I go back to find one of the sides if I have the hypotenuse? That's a good question, isn't it? So if you had a side length, one of the sides, how did you find the hypotenuse? You took that side and times it by the square root of 2. So how would you go backwards?
You square it, or no, you do the opposite.
The opposite of times, which is divide. So you would take the 3 and divide it by the square root of 2. That will get you backwards. Now, technically, we don't like to leave square roots in the denominator. Do you remember that? Technically, we don't. So we do have to do this thing called rationalizing. Do you remember how to rationalize? No. So it's actually not that bad. So what you're going to do is the goal is to get rid of the square root of 2 in the bottom. So if you times it by the square root of 2, what do you know the square root of 2 times the square root of 2 is? It's the square root of 4. And what's the square root of 4? 2. So what happens is essentially we get those square roots to go away. Now, you can't just go around multiplying a denominator by the square root of 2 unless you also multiply the numerator, right? So then the numerator is just 3 square root of 2. So this is 3 square root of 2 over 2. That's the sides. Yeah, that's both A and B in this case. Both of them. So another way to think about rationalizing is when you have something over a square root, the square root moves to the top, and then you just get rid of the square root portion on the bottom. So the square root of 2 moves to the top, and then the square root on the bottom goes away. It's kind of a quick way to do that in your head without having to write this every time, because you're going to rationalize a lot in this class. Yeah. All right, and then the last one, this is 4 square root of 5, and that's the hypotenuse again, right? So how do you go backwards to find a side length if you know the hypotenuse? You divide it by the square root of 2. So this is 4 square root of 5 divided by the square root of 2. And once again, you can't leave it like this, right? You have to rationalize. So we would times by the square root of 2 and times by the square root of 2. So what's the denominator going to be? Just a 2, right? Square root of 4, so just 2. And then the numerator is going to be 4 square root of 10. And technically, this does simplify just a little bit more, doesn't it? The 4 and the 2 can simplify, and 4 and 2 would make 2 square root of 10. So both A and B are 2 square roots of 10. And if you ever want to check, you can take the side and multiply by the square root of 2 and see if you get the hypotenuse, right? All right, what do you think? Super crazy? Doing okay so far? Much better when you have a side length to start with, right? Yeah, and then instead of the hypotenuse. All right, so would you like to know why it's the square root of 2 every time? Why is it the square root of 2, right? Like, why square root of 2? That's just random, you know? So I'm actually going to show you, okay? We're going to Pythagorean Theorem this. You ready? So if I Pythagorean Theorem and I pretend like I don't know this side, I'm just going to call it side C because it's the hypotenuse. I would set this up as x squared plus x squared is my hypotenuse squared, right? Pythagorean Theorem. What is x squared plus x squared? 2x squared is my hypotenuse squared. And so how do I just get the hypotenuse? You take the square root. So when you square root this side, the square root of 2 is just the square root of 2. The square root of x squared, because the square root and the square are opposites of each other, what's going to happen? And you're going to have just a x. So if one side is x and the other side is x, and you do the Pythagorean theorem, the hypotenuse is the square root of 2 times x. So the square root of 2 comes from when you add these together and you get 2 of them, and then you square root. That's where that 2 comes from. Kind of cool, huh? Yeah. Kind of like a neat, like, hey, that wasn't too bad to really understand where the square root of 2 came from. All right, here's the next one, 30, 60, 90, and this one I think is harder than the other one. And it's harder because the two sides are not the same length, right? So it's not like x, x, and one other thing. It's like one side's x, and then one side's the square root of 3 times x, and then the hypotenuse is 2 times x. So there's just a little bit more going on there, isn't there? So I like to go ahead and just say, all right, this one's the hypotenuse, right? And the hypotenuse is always the longest side because it's across from the biggest angle. 90 is the biggest angle, so it's the longest side. The side across from the 30, this is your shortest side because it's across from the 30-degree angle, the smallest angle. And so then this other one across from the 60, I just said that's the one in the middle, right? You have the shortest, you have the middle, you have the longest. Longest is also the hypotenuse. And that just kind of helps in my brain keep them all straight as opposed to be like, well, this is the one across from the 30 and this is the one across from the 60. And that's just too much. Shortest, middle, longest. All right, so everything is based off of the shortest side, everything. So in triangle number 1 down there, do we have the shortest side or do we have a different side? That 5/2, is that the shortest or is that is the shortest because it's across from the 30. So this is the shortest, which means everything is based off of that number, okay? So your hypotenuse is 5/2 times 2. And 5/2 times 2 is just 5. So your hypotenuse in this problem is 5. And then your middle side is going to be 5/2 times the square root of 3. And so you can just write that as 5 square root of 3 over 2. So that times by the square root of 3, that just goes in your numerator. And then that one's done. So when you have the shortest side, it's not too bad, right? Just times it by 2, times it by the square root of 3, you have all of your sides. So take a look at the second triangle, number 2. Do we have the shortest side or do we have a different side? Once again, we have the shortest, right? So the hypotenuse is 6 times 2, which is 12. And then the middle side, the square root of 3 times 6, so 6 square roots of 3. So once again, when you have the shortest side to start with, it's not too bad, is it? But when does it get harder? When you don't have the shortest side to start, when you have a different side. So number 3, we don't have the shortest side. Instead, which one do we have? We have the middle side, all right? So the middle side is the one we have. How would we get back to finding the shortest? Because once you know the shortest, the hypotenuse is easy. So if you have this one, how do you go back to the shortest? If you went from the shortest to the middle by timesing by the square root of 3, how would you go backwards? Divide by the square root of 3. So you're going to take this number and divide it by the square root of 3. And that looks really ugly, doesn't it? Yeah. Do you remember how to divide these when you have a fraction divided by something else? Technically, you can write this one over 1 as another fraction, right? Do you remember what to do when you have a fraction divided by a fraction? Yeah, so you actually take the bottom fraction, you flip it. I don't have any more space. You flip it over, so instead of square root of 3 over 1, it'd be 1 over the square root of 3, and then you multiply instead. So if you're dividing by a number, you have a fraction divided by a number, flip it and multiply instead. So in the numerator here, you would have 7 times the square root of 3 times 1, so just 7 square root of 3. In the denominator, you have 2 times the square root of 3, so 2 square root of 3. And what's going to happen with those square roots of 3? Yeah, because you have it times in the top, times in the bottom, so we can say see you later, and we just have 7 over 2. So our short side is 7 over 2. So then the hypotenuse, 7 over 2 times 2, which is just 7. So when you have like the middle side or the hypotenuse, go back to your short side and then use that number to find the other one. All right, so number 4, which side do we have? We have the hypotenuse. So how do I go from the hypotenuse back to the shortest side? Divide by what? Well, how did you go from the shortest side to the hypotenuse? By 2, right? So how do you go backwards? Divide by 2. So depending on which side you have, you might divide by the square root of 3 or divide by 2 to go backwards. So that would make that what? 5 square root of 3. So your short side is 5 square root of 3. So now you have your short side, you can find the middle side, right? What do you do with the 5 square root of 3 to find the middle side?
You multiply square root of 3.
Times it by the square root of 3. So 5 square root of 3 times the square root of 3 is 5 square root of 9. What's the square root of 9?
3.
So what's 5 times 3?
15.
15. So that middle side is just 15. So in this class, we're going to do a ton with the square root of 3, the square root of 2. You're going to see those two values come up like all the time. Square root of 2, square root of 3. They're just going to be all over the place, all right? All right, so that's it. So it's just the that one additional page that I gave you, which is just practicing the 30, 60, 90, and the 45, 45, 90s.